So good morning, everyone. My name is Sara Canedo, and I will be your moderator for today. So our webinar is called How Digital Twins and AI Are Revolutionizing Manufacturing, and it's our last webinar from our webinar series. So first of all, thank you all for being here, and also thank you to our speakers for participating and being here today. So our series is called Next Gen Materials Europe's Digital Manufacturing Leap, and it's a part of 5 webinars with 3 key projects on manufacturing. Our key takeaway for today, it's digital twins and AI that are transforming manufacturing, as you know, by enabling real-time simulation, predictive maintenance, and system-wide resilience through seamless data integration. Our focus will be to explore the role of digital twins technology in advancing in the resilience of manufacturing systems through data integration and simulation, and also AI-related part in revolutionizing manufacturing. About some obvious benefits, combining digital twins and AI enables real-time monitoring, simulation, and intelligent decision-making. Together, both of them, they help manufacturers predict issues, optimize processes, and adapt quickly, boosting efficiency, quality, and also system resilience. Some KPIs that we can mention here: it reduces downtime, it increases equipment utilization, improve product quality, also a faster time to market, lower operational and maintenance costs, greater system resilience, improve sustainability, energy efficiency, and also more accurate forecasting. So these are the ones that we think they are the more important KPIs for this subject. So this part, with these webinars that we are presenting, our EU goal is enhance industrial competitiveness through digitalization. Our key strategies, we have 2, the Digital Europe program and also the European Industrial Strategy. And we want to align the EU strategies with digital tools in advanced material manufacturing. Our vision in this part is more agile, efficient, and resilient European industry. So these are our objectives when pushing for digital manufacturing in Europe. So this, as I told you before, it's the 5th webinar of a series of 5. So I will not ask you to join the next ones. Maybe we will have them, but for a different series. So I thank MetaFacturing and Pioneer to be here, and I make part of the DiMAT project. Our presentations will be 3, will be divided in 3 projects. So for DiMAT, we will have introduction of key trends in digital twins for manufacturing. For MetaFacturing, we will have digital twins in casting and welding. And for Pioneer, we will have role of digital twins in the Pioneer project. Then our beautiful speakers, we have Giorgio with us from NTUA, representing the DiMAT project, also Lydia Mavraidis from NTUA, also Milosz from Hegla-Hanic, also from DiMAT. Then we have Juergen Freund from Benteler Automotive Components, Peter from LTH Castings, Iason from Core, and myself from F6S Innovation. So thank you all for being here. We have a full house today. So now for this webinar to be a little bit more interactive and also to be interesting for you, we prepared a couple of questions for our speakers. And I will start with Giorgio and Lydia. So the hot topics for today, of course, it's digital twins, AI, data integration, and simulation. So Giorgio and Lydia, in the simplest possible terms, what exactly is a digital twin in the context of manufacturing, and what is its core purpose? You are free now to answer.
Okay, first of all, hello everyone, and thank you, Sara, for introducing us and for hosting this meeting. So generally, a digital twin is a virtual representation of a physical asset or a process or a system in general. What it tries to do is to actually mirror the real-world behavior of that system in real time. So in order to do that, it needs to have connectivity to IoT devices, to Internet of Things devices, or to sensors in order to collect live data from the shop floor, since we're talking about the manufacturing domain, And this in turn enables the manufacturing stakeholders to monitor, analyze, and optimize any operations without having to directly interfere with the physical asset or the physical process. Now, the core purpose of a digital twin is to actually bridge this gap between the physical and the digital world. And this allows the companies to understand what is happening on the factory floor. It gives them the opportunity to predict any potential issues in the context of predictive maintenance before they actually occur, and assist in the decision-making process by providing simulation and control strategies. And this, in turn, provides a very dynamic and data-driven view of the equipment and the processes. And so the digital twin is a very good tool in order to improve the efficiency, to reduce downtime, and increase the overall productivity in the manufacturing domain.
Georgia, you want to add something to this clear question? No, answer.
I think my colleague described it very nicely and clearly. So, yeah, I don't have something to add. Thank you.
Thank you very much. I can move now to the second question for Juergen and Peter, related also to digital twin. So how does a digital twin fundamentally work? And can you explain how it uses real-time data to create a living virtual model of a physical asset or process? So maybe to divide this into questions.
Mm-hmm. Okay, I will concentrate on the model-based digital twin. For us at Benteler, the digital twin is a 3D model with dynamic behavior for simulations, behavior based on the real-time data or a real robot program. Right? So our company, Benteler, is an automotive supplier, and for every product we have to produce, we have to set up a production line. And so we concentrate on digital twins in the production cells or production lines. So in the beginning, our digital twin is only the geometric representation, and during the planning process, it gets smarter and smarter and smarter. So in the end, we can combine it with the real robot program, and so it's a real representative of the production line or the production cell, which is later set up in the real production plant. And the digital twin, before we set up, it's a basic for us to discuss it with the customer or with our supplier, so that they see what do we need and how does our production cell work, and so they can see and help us in the setup of the production lines. And on the other side, we need the real-time data. And at Benteler, so every equipment in our plant is connected per OPC-UR to a time-based database. It's a smart production database, we call it at Benteler. And there we store every sensor data and every machine data in real time of the plant. But it's not really real time, it's 10 hertz or 1 hertz. But we have this information of every sensor and every machine and every line. And I can go from my desk to every line and see what are the data of the special machine in this line. And we have then set up a possibility to read all the data which are in this database, and we can connect then the virtual model in visual components via OPC-UR to our database, and our database is connected via OPC-UR to the real machine. And we have a small delay. It's not really real time, but seconds later we have the real data which are at the machine in the plant, and so we can have like a time warp. So we can set up the situation at a specific time stamp and see what happens there, and then we can start the simulation after this timestamp in order to see what will happen in our simulation. So
thank you so much, Juergen. Peter, do you want to add something?
Yes, of course. Thank you, Juergen, for this brief, detailed explanation. I must say that automotive, we are both automotive, Benteler and LTH Castings. I'm from LTH Castings. We are 100% automotive industry, and this automotive industry is pushing us always under pressure for new innovation. We have constantly to evolve to be competitive on the market. And we are using digital twins for more than 15 years in our company as a standard solution to do at first for technical feasibility studies, and then later on to determine the process parameters which we need to apply to the machines on the shop floor. This is a standard in the industry. Now, what we are aiming with our project is to bring all this data that we have on the machines, which is like more than 1,000 parameters. You can imagine all the machines today, they're already smart. We don't have basic machines. They're all pretty much connected with a lot of data, a lot of information, and they can already decide on their own what parameters are good and what parameters are bad. This is a standard in the industry. But to take it on the next level, we merge together product data that we have from the end of the production line and machine parameters data that we gather on the big data scale from our machine park. And if we merge this process data with the product quality data, then we can find better ways that looking from the correlations between the quality of the product and the parameters, we can be even smarter than the machine itself. So this is our aim with this project.
Thank you so much for the clear presentations and insightful. Now I will move to the third question to Iason. So Iason, looking at the current manufacturing landscape, why is it the concept of a digital twin becoming so increasingly crucial for companies? And what is the biggest driver behind its growing adoption?
Hi, everyone. Thanks again for the invite to this webinar. So first of all, we have heard a lot about the fourth industrial revolution, and we have seen the effects of the rapid acceleration of the research and implementation of AI and the benefits and the disruptions that it brings. So as we have witnessed that in real time, we also companies take notice. So they also take notice of the benefits and the value they can bring to their operations. So without further ado, the main reason for the digital twins steadily becoming more crucial in manufacturing right now comes to the benefits of efficiency, precision, and most importantly, risk reduction. We have as an enabler the simulate before you try, so you can identify any potential issues, bottlenecks, and any other disrupting factors in a data-driven manner without even investing into new equipment or process lines. Now, for processes like WAM or SMC, where you're dealing with complex setups, expensive materials, and machines that need to run at peak efficiency, every mistake will cost time and money. And the markets that are becoming increasingly competitive, the margin of error is getting smaller and smaller. So what a digital twin gives you is a complete virtual replica of your process, as the other speakers have hammered the point, I believe. So you can simulate different scenarios, optimize parameter, identify and predict failures, and make adjustments before you even touch the physical asset. So that translates to fewer errors, less downtime, and faster development cycles, and more reliable outputs.
Thank you, Iason, for your answer. We can move to the last question now from Milosz. So, as a company in the glass processing industry, could you share the key benefits that a manufacturing company can expect to see from adopting this technology, and also what's the core value proposition that makes it so important in the current manufacturing landscape?
Yeah, sure. So let's just think about everything from business perspective. So then the main goal for a production company is to bring profit, obviously, so to earn money. So if we think about small or medium company in glass industry, we can just assume that the revenue could be, just our assumption, 1 million euros per month. And the company earns 10% from this revenue, so it would be then 900,000 euros are the costs for the company. So I saw also some of the companies in our industry where glass is approximately like 50% of total costs. So then if we calculate it, it's 450,000 euros just in glass. So what company can do is to change the optimization process. Optimization process is basically routine. So glass is delivered from vendors as production sheets, as glass sheets. At the most popular size, it's called jumbo size. It's 6,000 millimeters wide and 3,210 millimeters height. So it gives a little bit over 19 square meters of area to cut. So then we got all the customer orders, and they are mixed all together to cut the glass together. So to minimize all these wastes, obviously we'll try to mix as much as possible. But in the end, there's just no possibility to use all the 100% of raw materials. There is always a waste because just the sizes of glasses are different, and that's just part of the process, and that's part of the business. So just for our discussion, let's just assume that we can use 80% of all raw materials. So it's called yield. And then we get this 20% as a waste. So if we calculate 20% of all glass costs altogether, so 20% of 450,000 euros, it gives us 90,000 each month. So this is the value that the glass is thrown away to the trash cans. So if we multiply this value by 12, it gives a little bit over 1 million euros per year. So this is something that we lost, and there is no chance to get it back. So what can company do is to change some of the factors, how the optimization is performed, how we mix orders together. Maybe we could change some algorithms for the optimization. There's multiple different things that could be done. But the problem is that each of these changes will affect our real production. And obviously in the manufacturing environment, this is never a good idea to do it directly on live environment. So this is when we got digital twin in action, that we can basically run all these simulations with real data with no impact on real production. So everything could be tested before all changes are performed. So it will change our quality in the future because we can predefine what will be the impact on the glass sheets. It will have an impact on schedule because maybe after the changes, it will take longer for operators to score the lines on the cutting tables. And also it could change also a little bit with the complexity of production. So all these things need to be taken into consideration. So that's why it's much better to do it using a digital twin than directly on live environment. And obviously, there is always a limit that some changes could be performed. So sometimes there is just no way to change parameters. There is another option we can do. We can try to increase the volume of our production. So if we accept this 20% of waste, that's fine. So what we can do, we can obviously try to produce more. So again, we can change capacity formulas. But again, that's probably not the best idea to do it directly on live environment. Then there is again digital twin in action. After changes are tested, we are 100% sure nothing wrong is happening, then it's time to implement everything on live environment.
Thank you so much to everyone that's answered. We have to move for the sake of time, but thank you so much for all your insightful answers. So we will start now with DiMAT for Georgia, Lydia, and also Milosz. So the floor is yours.
Okay, so this was just a very introductory slide. I think most of these things we already discussed on them previously, but just to sum everything up, a digital twin is a virtual representation of the physical asset. It needs connectivity to IoT devices. It has the purpose of bridging the gap between physical and digital worlds, and it gives us the capability of making predictions and assisting in the decision-making process. So in the next slide, we try to focus. Sara, if you don't mind, can we move to the next slide, please? Thank you. Let's just focus now on the digital twin for process control, which is the tool that NTUA developed for the DiMAT project. So the DTPC tool is a set of digital twins that support the virtualized functions as an abstraction of the IoT devices that are involved in the respective DiMAT suits. It monitors the process in which the devices take part, and it gives access to simulation and emulation algorithms. It has communication and interaction with the physical devices, although the main functionalities are actually provided through the digital counterpart, and we haven't focused so much on the actualization on the actuators of the digital twins. And also, it has a very modular, secure, and easily deployable design, and it is developed using only open source software. So in the next slide, we have the main functionalities of the DTPC toolkit. First of all, we have a monitoring, which means that the DTs collect and process time series data that are collected from the IoT devices. It has communication and control capabilities, so it interacts with the physical devices. It also has the capability of realizing forecasts with different techniques like ARIMA or LSTM. These things are also going to be presented by Georgia following. Alerts are also a capability that we have offered in order for the user to set customized thresholds for the different metrics that are monitored by the DTs, and he can receive notifications whenever these thresholds are exceeded. And also we have integrated some dashboards and some visualizations in order to make it easier for the user to monitor the different metrics of interest. Now, in the next slide, we see that within the DiMAT context, the DTPC was a tool that two different pilots showed interest in. The first was the composite pilot and the second the class pilot. So we also had some more customized functionalities for these two verticals. For the composite pilot, we had a prediction use case. We needed to predict the process success, so the quality of the outcome product based on some experimental setups. For example, the skill of the operator, or the delays in the production, or the state of the machine. Whereas for the class pilot use case, we had to predict the potentially defective equipment based on some preheating and heating temperature data that was provided by the sensors. So next, my colleague Georgia will say a few words about the architecture of DTPC and also give you a very short demo, live demo. Thank you.
Yes, hello. Can you hear me?
Yes.
Okay. So concerning the architecture of the DTPC, the toolkit is based on the NFL virtual object software stack, which is open source and consists of virtual objects and composite virtual objects. So virtual objects represent individual IoT devices or processes. They support specific virtual functions depending on the equipment or process they twin. And we have also the composite virtual objects, which combine multiple VOs into a more complex digital twin to model the entire system. They are focused on allowing flexible updates without impacting the rest of the system, thanks to the microservices-based architecture. Can we move to the next slide, please? Thanks. This is the high-level architecture of the composite pilot in DTPC. There are some data loggers for pressure, power, and temperature, which feed the information into a composite virtual object. Each logger first checks rule violations locally and sends alerts if any thresholds are exceeded. The composite virtual object gathers all this data, performs some forecasting algorithms and status updates, and then forwards the relevant outputs to backend scripts and to the user interface. In the next slide, we have the glass pilot architecture of DTPC. The fairness sensors here provide temperature data, which is stored and analyzed first for threshold violations. And there's also a dedicated plot virtual object that generates the 3D visualization of the furnace's internal temperatures. So both these virtual objects send the data to a glass composite virtual object, which aggregates the information, does the forecasting techniques, and updates the user interface. So is there any time to show a short demo for the glass pilot? Can I share my screen?
Yes, of course. Go ahead.
Okay. Okay, can you see now my screen?
Yes, perfectly.
So here we have the main functionalities of the DTPC for the glass pilot. A user sorry, let me reshare my screen. Sorry, I have to run. Okay. Okay. Yeah, I don't know why it doesn't show. It was supposed to show the measurements provided by the sensors measuring temperature inside the furnace through a Grafana dashboard. The user can also set the acceptable temperature ranges, publish the limits here. Sorry. And through the live monitoring button, see those ranges are violated in the sensor measurement. Sorry, maybe the VM is down, so I can't really show the demo. I'm very sorry for that.
No worries, Georgia. Is there something that you want to present specifically that it's not related to this page?
If you give me 2 minutes, maybe I will restore it.
Okay, no problem. Maybe we can pass to Milosz, and then we can come back to you, maybe.
Let me give it a try once more.
Okay.
Yeah, it doesn't work. I'm really sorry about it.
No problem. Those things happen. When I can move, just tell me.
Yes, please move on.
So let me just share my screen again. Slide. Okay. Sorry, I'm not sharing my screen. One moment. Okay. Let me just. Are you seeing my screen?
Yes, we do.
Yes. So Milosz, go ahead. Floor is yours.
Yes. So just quickly, this is extension to something we discussed just a moment ago. Standard production flow in glass industry, and basically simple processes that most of the companies perform is cutting, seaming, and tempering. This is, I would say, 95% of the industry use at least these processes. And imagine situation that we got quality issues in the last process. Furnace, obviously, this is something quite complex, and it very frequently generates multiple different issues. There is a wide range of glasses to temper, each different thickness of glass, between 3 and 19 millimeters, different type of glass, either it's clear or it's tinted. There is color, there is spandrel, enamel, a digital print, whatever is that. If there is any code like double or triple silver, it requires changes if it comes to the parameters of the furnace. And obviously, the problem is that each recipe is unique and it requires a lot of skills from customers to perform it. So obviously, it leads to the problem that the process is complex and could generate a lot of quality issues. So what we can do in terms like quality department decide, for example, to screen what's the problem with that. And again, as we discussed, this is not the best idea to perform this kind of tests directly on live environment. So then again, we got the digital twin that could work simultaneously to our production. And it could pull information directly from our database. Usually it could be like SQL database that we use not for live, but also we can copy and create another digital twin that contains exactly the same information as our original live environment. And over there, we can basically have a playground to all these decisions. Obviously, part of the business is also trying to find all continuous improvements. So this never ends. And then digital twin is the source of all this deep and analysis and the information for either quality, for engineers. What could be done? Maybe we can switch to another table because the quality of edges, it's not good enough, and it increase all the remakes from cutting tables. Maybe the process needs to be changed because seaming is like a very basic edge modification that edges are not so sharp, but maybe we could do more. Maybe we should grind these edges because then the quality is much, much better and it could improve our furnace outcome. So all these questions, all these doubts, it could be answered over here. And there is no risk that all these additional tests, all these modifications can impact anyway our production data. So that's the answer for the companies in manufacturing to try to find all improvements day to day and trying to find, obviously, from business perspective, much more profits, because they can save some costs, but also from the brand's perspective to increase the quality. So also for business, it's not just about money, but it's also about the brand. So digital twin will be also good way to answer all these needs and requests from the companies.
Thank you so much to the three of you. Maybe we can move to the second part of the presentations, which is from MetaFacturing. So I will let you share your screen. Juergen or Peter will share screen, right? Sorry, you're muted.
I'm working on it.
It's okay.
Okay, can you
We
see
can
it?
see. Yes, perfect.
Okay, before we start, okay, our theme is digital twin in welding and casting in the project MetaFacturing, and I will give you a short introduction to our project. So in MetaFacturing, we have the goal to improve our production. As a company, it's always our goal, but we have a lot of data in our processes. So you can imagine we have the production process. In the production process goes the material and the process parameter to start the production and to, for example, the welding parameter, the speed of the robots and so on. And then we produce our product. And when we produce the product, we get a lot of data. We are collecting this data from all the sensors in the process. And we get results from the quality tests. And we collect this data and we put all this data together in order to get a view on the quality of the product, so that in the end we can improve the quality of our products, so that we have less scrap, we have a better output, and that we can trust the data, so that we don't need any destructive tests, and so we have less scrap, and so we want to improve our production process based on the data which we get from the process and we put into the process. And we want to see how looks such a process in our company. Here we see the welding process. We have the goal to improve the welding of a battery tray, and you see it's a very big welding cell, and there you have two robots which are welding such a battery tray. And we set up or in the beginning of the project, we had this digital twin of the production. So when we plan the company or we plan the production line, we set up such a virtual twin in a 3D environment. And after the welding process, we have the scanning of the weld seams. There we get additional data from the scanning process, and we look at every weld seam and we analyze every weld seam, and we can say it's okay or not okay. And after that, maybe there can come a physical destructive test, and it's called microcut, where we analyze the weldings. So you can see, we see during the process, we get the welding data like current and voltage. Then we get the weld seam scan from the optical inspection test. And here we have real weld seam, how it looks like when it's okay. And hours or after the welding, some battery trays go to the microcuts. That means we cut a weld seam in order to see, is this weld seam okay and not okay. And when we can trust on the data, then we don't need to destroy such a battery tray in order to see the quality. So that is our goal, that we identify defects and their root causes, and then we can improve our welding process by improving the parameters, and in the end we increase the weld seam quality and we reduce microcuts and scrap, and we increase the quality. Yeah. And in our project we take we select 3 parallel welding cells so that we can compare the different welding cells, and we have an optical inspection cell from Vitronics where we inspect the results. And here left you can see the weld the microcut inspection. It's today done by hand, but in the future it will be done by artificial intelligence, and we get automatic cutting of this microcuts. And you see, we get a lot of data from the different sources, from us, from Benteler, from the Fronius power sources, which the welding, from the Vitronic scan, and we collect all this data in a database by risk, and they are running the machine learning algorithm on this, and they make the data fusion so that all the data are on the time base and this at the same time base, so that we can compare them. In order to see what we do with the digital twin, so in the beginning at Benteler, we planned the production lines with some digital twin. We have a library with all of our production items or production equipment, and so we can very easily set up a production line in order to see what equipment do we need in this line, how is the dynamic between the cells, how is a handling robot working between the cells, and what is the worker doing there. And we can improve the process to get a better OEE, to test the welding speed. And one important part is to see the clearance of the welding torch. You see it in this picture down there. You get a cloud of all the welding torches, and you see is there a collision with the robot or with the welding jig or with the welding cell. And so you can improve the process. You have no failures in the process before you set up the real welding cell. And in the project, we have then the real production cell, we have the digital twin of our cell, and we have the real robot programming. And we are loading now the real robot programming or the actual programming in the digital welding cell. And on the other side, we are recording from the robot the position of the robot by the KUKA RSI. And so we can compare in the future, is the real robot path the same as the programmed robot path? Are there any changes, and can we improve this weld theme, for example, the position of the robot here in this example? And on the other side, one big feature is the simulation of the welding. This is done not with visual components. For this, we need, for example, Simofakt welding, where we can simulate the welding process in order to see what is the heat impact of the welding torch and the welding process, what's the impact of the speed and the distance and the angle of the welding torch, and what we can, or what we work is that we can see from the simulation how is the penetration. And so we can trust our welding parameters, so that we can say we have this welding parameters and then we get this penetration. Because in the beginning you see this microcut on the right side. If the simulation and the microcut is the same, then we can say, okay, we can trust on our input parameter and we don't need any microcuts. And that's the goal in this project. So that's an overview of the digital twin in the area of the welding, and now we can go over to Peter to see what we do in the area of the casting process.
Thank you very much for your presentation. We are seeing your screen, Peter. You're muted. Yes, maybe now.
Okay, so
Perfect.
Thank you. In the aluminium die casting, our main challenge problem is the porosity of aluminium, which is due to the fact that aluminium casting is done under pressure within the tool. On the right side, you can see what the typical constellation of the die casting cell looks like. In the middle, the die casting machine, and then the peripheral equipment on the sides of the machine. And we gather all the data from this, or the main machine, or the other machines attached to this. So at the end of the line, in the aftermath, we have a long reaction time to detect a defect. So after the die casting, we do a machining, we do washing, and we do also the leak testing, which is a 100% control of the leakage, also related to the porosity of the part, or even some other reasons for this. And our basically, as I mentioned already in the forum before, the machines are all smart. So they enable monitoring of all main process parameters. We have defined the levels of the parameters that are good and that are not good, but the errors occur as the parameters are not linked between each other on a linear basis. And looking at the I'll jump to the third slide. It's a nice picture here on the right side top. You can imagine we have the parameter 1, parameter 2 on the machine defined the good value, the green value of the parameters for 1 and 2. But at the end, because of the correlation between the two parameters, the good parts are not linear in this square, but are in some kind of cloud. And if you take into account 1,000 parameters that you have on the machine, this is our aim to find the most influential parameters and merge them together. So our idea, already mentioned before, we have a model-based manufacturing. We try to, the model is defined via MagmaSoft simulators. And the parameters are then put on the machine. But our goal here is to align it also with the data from the machines and the quality defined checks, 100% quality control checks afterwards, and to merge this all together, all this data together, and apply artificial intelligence on top. So how we did it, we implemented QR code tracking of the product throughout the complete process flow within our company. It is scanned on each product station, and the parameters are linked to the product. At the end, we define the product's quality, and this can be then linked between the parameters and the quality. Our goal is to determine the statistical correlation between the product quality and process parameters. And at the end, this should be this is able to be in real time seen on the production shop floor. So basically, we can have the alerts on the shop floor when the machine is machine is producing bad parts. We could already see that alert for this from the parameters. So the solution which we put together within our MetaFacturing project is we applied machine learning algorithms to the parameters evaluation and quality prediction, so that so to say future importance, so that we define which parameters have the most influential on the quality of the part. Also taking into the account the correlations between the parameters. So you can come to the top 5 to 10 parameters, which you then take into the model. And then with AI model for declarative programming, we apply statistical approach and the logics to determine from the parameters with the best correlation to the quality which product coming out of the die casting machine will be leaking or will have porosity, and which one is a good one. So our pilot results show us that we are on a good track. We are able with the model, in case this is a significant measure, the porosity on the product, we can detect 50% of the bad products based solely on the casting parameters, which the machine was treated initially as okay. So this is we could reduce with this our scrap rate, and we could basically stop the process immediately and correct the parameters in such case online. Yeah, this is the current status. We're putting the model now on the production shop floor from the pilot, and hopefully this will be up and running by the end of the year.
Thank you, Peter, so much for the presentation. Let's now move to the last one from Iason. Let me just share my screen. You can see my screen, right?
Yes.
Great. So, Iason, the floor is yours.
Yes. We first move to identify what is the, let's say, what is a digital twin? What parts comprise a digital twin? We have the physical layer, which is where the real-world systems reside. There can be machines, sensors, actuators, irrespective of the manufacturing process. On top of that, we have the communication layer. All of these machines and sensors produce data, so we need to have the communication layer where connectivity happens and resides. We have IoT networks, standard industrial communication protocols, and wireless links. On top of that, the digital layer resides where there is the raw data acquisition and data preprocessing functionalities occur, and basic system digitization is happening. Building on top of that layer, we have the intelligence layer, where we have advanced analytics, machine learning models, simulations, and decision support systems are being deployed and developed. And finally, we have the application layer, a way for the user to interact and be informed of this system, where we have real-time monitoring, predictive maintenance, optimization pipelines, and user-facing interfaces. Moving on to the next slide and starting with the communication and digitalization layer, we have the asset administration cell that we are utilizing on the Pioneer project. So the asset administration cell is one of the most important syntactic components of the digital twin architecture. Essentially, it allows in a standardized way to have a digital representation of any kind of asset throughout its life cycle, have an interoperability and abstraction, both in semantic and concept distributions of the system, to leverage the existing knowledge, research results, and advance the representation of the physical assets, manipulation of the information to the related product, process, and resources concept. And all of this communication and update of the digital representation occurs in almost real time. So the asset administration cell can interface with various different data sources. And finally, it allows the knowledge transfer and the reproduction of manufacturing scenarios. Now, on the next slide, we have the specific needs that we have of the AAS within the Pioneer project. So the use cases that we tackle have a heterogeneous environment. So we have from material characterization all the way to the manufacturing stage. What AAS allows us is to have the seamless interoperability within the framework of Pioneer. We have a structured and secure way of data exchange between equipment, robots, machines, and edge devices that comprise the solutions of Pioneer. AAS is compatible with the most used industrial protocols such as MQTT and OpenCQA, of course, supports even more protocols. Like I previously mentioned, we do have reinforced communication in real-time data handling procedures. So it ensures continuous data flow and supports automations. And it also provides the end user with insights about the sensor specifications and data acquisitions. No, for the implementation of different necessary processable products, we have, for example, for the WAM use case that we deal with in Pioneer, the robot and deposition head, the WAM process itself and a variety of products. And for the SMC use case, we have the SMC and mold, the process itself, and the double ARM wishbone that we have implemented in the asset administration itself. I have also put some images as an example to see from the process on the most left side down to the toolheads and finally to the end result products. So AAS is adaptable to various manufacturing scenarios and processes, and it can be customized and tailor-made to the characteristics of its unique use case. Finally, for the next slide, please. Thank you. Finally, the potential application of areas from the AAS in industry and research. So essentially, AAS enhances collaborative development and planning, have seamless exchange of asset data. We can optimize design compatibility and sustainability efforts while recording each step on the way. Also, we have resilience in rapid changes. It serves as a structured information model that integrates AI-driven scheduling agents and also supports network 5G-enabled factory components. And finally, the most important feature is the vertical and horizontal exchange of knowledge. By offering a standardized digital interface for both hardware and software agents, it enables the skill-based service robots to share capabilities, runtime, status, and control function. Moving on to the higher level, we start our journey with the reduced order models, which are based on a simplified version of a high-fidelity simulation that simulates a physical phenomena or process. The approach, the why behind the reduced order model is to reduce the computational expensive operations of a full fidelity simulation. So the way we achieve a reduced order model is that we extract the dominant patterns of all features via various mathematical techniques, for example, proper orthogonal decomposition or tensor rank decomposition. We then can construct a lower dimensional approximation of the original system, and we can finally solve this reduced system much faster than the full resolution counterpart. In the Pioneer project, we have two use cases, the Marelli use case, which is the SMC process. So we have developed a ROM model to enable real-time analysis of a process outcome and rapid design iterations. And for the MX3D use case, we can explore a wide range of simulation parameters and find the appropriate combination that minimizes the difference between simulations and experiments. Finally, some trade-offs of and advantages of the reduced order models. First of all, we have as an advantage the speed. We have drastically reduced simulation time. It's an ideal model to deploy on the machine itself. It's ideal for control systems and optimization loops. And of course, it doesn't require much computational needs. So it's suitable for embedded systems. But we have some disadvantages and limitations that we have to consider. First of all, there is the accuracy loss, since we are dealing with a reduced order model. It may not capture all dynamics, especially for nonlinear applications. So by increasing the accuracy would mean increasing the number of snapshots of the reduced order models. And it is not a servability, it's a problem-specific development. And also they require retraining or retuning from different configurations. They're not universally transferable. They're built specifically for this specific phenomena or process that they describe. And there is a development overhead, which requires an upfront effort, snapshot selection, model extraction, and a lot of computational time. Now, moving on to the data-driven model aspect. Data-driven model is essentially a predictive model that is built using empirical data, completely disregarding physics principles. It identifies patterns, correlations, and system behavior by learning from the historical data. They're widely used in high-fidelity physics models where are unavailable. We have a lot of sensor, process, or experimental data. Common use cases include predictive maintenance, process optimization, fault detection, and digital twins. The way it works is that we first need to collect historical or real-time process data, so a data collection campaign needs to happen first. We train a machine learning model to map inputs to the outputs so that we have the desired outcome. And we then use the trained model for prediction, monitoring, or even control. Now, for the Pioneer project, for the Marelli use case, the developed data-driven model offers recommendations to the operator based on the previously correlated parameters with the quality measurements. And for the MX3D use case, it monitors and identifies in near real time any potential wrapping or cumbering effects that could occur on the printing job. Now, of course, we also have some, next slide, please. We have some things to consider with data-driven models as well. First of all, okay, the advantage is that we do have faster deployment in comparison with ROMs. There is no need for fulfill physical understanding. There are adaptable models. The models can evolve with new data, and they captured directly real-world variability. But there are also disadvantages, such as there is data dependency. The quality and quantity of data directly affect the performance of the model. The models are limited in their extrapolation capabilities. They have poor performance outside the training range of their data. And we also have black box behavior. They are not interpretable by definition in comparison to physics-based models. And the limitations are that it's a huge requirement to have historical data. If we don't have sufficient number of data, we can't proceed. As with ROMs, they are system specific with specific objectives and systems in mind developed. And there is also a maintenance overhead where periodic retraining as process conditions change need to occur. Finally, we move to the hybrid digital twin, which is the focus of the end result of the Pioneer project. Next slide, please. So what is a hybrid digital twin is essentially a combination between physics-based model and data-driven approaches. So we combine the strengths of the reduced order models, where they're ideal for real-time physics consistent predictions, but they are limited for non-process variability or maybe missing dynamics of their own. And data-driven models can cover these gaps by learning from the real-world data. They're adaptable and responsive to the evolving processings, but they do lack the physical guarantees and generalization outside the training space. So the way it works is that ROMs capture the fundamental system behavior, and the data-driven component learns the unknowns and certain intra model effects using machine learning approaches. So they combine models updates in real time with live data from sensor systems. Next slide, please. And the advantages and considerations of the hybrid digital twins are as such. First of all, we combine the best of both worlds in comparison with data-driven models and ROMs. So we have reliable physics and flexible data-driven learning. We enhance the accuracy of the overall digital twin because we capture both known system behavior and unexpected patterns. We have real-time insights. We can have monitoring, control, and optimization based on live data, and they are more robust. And since they're more tolerant to variability and uncertainty than purely machine learning or physics models. But the considerations that we must take into account is that it has some additional overhead in the development efforts. It requires the integration of both model families with the system specifics. Again, we have the data requirements because we have the data-driven component. Computation overload, since in order to derive a ROM, you need to have a full fidelity simulation. So there is an initial computational load that needs to be taken into account. It is a tailored implementation, so it's not a generalized solution. And you need to trade off the balance between physics-based model and data-driven models. And of course, there is also the maintenance overhead that we inherit from the data-driven models and also for the ROM. But the benefits, I would say, outweigh the considerations. And that is all from my side. If you have any questions, I will be happy to answer.
Yes, if someone has any questions, please write on the chat or raise your hand. Otherwise, we can wrap up this wonderful last webinar because we passed 10 minutes from the limit time. So if no one has any questions, the session will be uploaded on our YouTube channel from DiMAT. You can also visit the pages of the Pioneer project and MetaFacturing project, which are present in LinkedIn, and also their websites, which will be shared in our social media also from DiMAT. And that's it. Thank you all for coming, and I wish you a wonderful weekend, and thank you to all our nice, wonderful speakers. Bye-bye.
Thank you.
Thank you. Bye.
Thank you very much.
Thank you.
Bye.
Bye.
Bye.